So we have our solution to the advection dispersion equation, and we've talked about the fact that it's a Gaussian form. But one of the things we haven't talked about yet is the impact of sorption. So we see this R showing up over and over again. In fact, it shows up in exactly 3 places. The R is called the retardation of a plume. And this is only going to find this form when we have what's called linear sorption. And what that means is that the sorbed concentration versus the liquid phase is going to have a linear relationship. So there is a constant so that the concentration on the solid phase is equal to some coefficient times the concentration in the liquid phase. This description of sorption is very accurate for low concentrations. Why is that? Basically, we have a solid here I'll draw, and it has these sorption sites. And so there are many, many places that are chemically reactive where our solute might sorb. Now, what happens is, when there's low concentration, maybe one of them gets a solute stuck to it, but that leaves all the rest of them open. So having one site occupied does not greatly change the probability that any other solute molecule might also sorb. On the other hand, if we had many, many, many of these sites occupied with sorbed compounds, then we'd say, what is the probability that another solute would have a place to bind? And it becomes very low. So when all of these are filled up, then you would have no sorption. So what we see then is that linear sorption, when there's only a few sites, then the probability of new sorption is held constant. But as we get to higher concentration, in fact, this curve goes to a maximum, which is the total, we use a Q typically, is the total sorption capacity of that material. So when we're at the low concentration end, then we can work with this concept of retardation, and we can think about it as a linear process. This is very important because when it goes to the nonlinear stage, then all of the mathematics behind this changes drastically, and this idea of retardation is no longer suitable. Supposing we do have linear sorption, what we see, which is really, really cool, is that the R here, there's one more R, the R universally is found with a T. Again, setting aside degradation for the moment, but in this part of the equation, it's always T over R, T over R, T over R. So all of the time is adjusted by the retardation factor, which means that for the plume, if with no retardation, the plume took T equals, let's say, 1 hour to get here, and if the retardation factor were equal to 4, then for the retarded plume to get to the exact same place would take T equals 4 hours. So the retardation really does just slow down the movement of the compound, and it's very predictable. And the other thing you'll see is that R here means that as retardation gets larger, the concentration in the liquid phase is smaller. And so it reduces the amount of, and because, of course, 4 times as much now here is sorbed to the solid than is in the liquid phase. So the concentration follows the exact same pattern. The geometry is the same, but it'll have a lower concentration and it'll move more slowly. And that's why we call it the retardation factor. And that linear description of how solutes move in soils is a very, very handy description, and it's useful for many compounds which are important at low concentrations.